A particle in an isolated potential well occupies a fixed, unchanging energy level. In static quantum mechanics, the Hamiltonian is constant, and the probability of finding the particle in a specific state remains unchanged over time. But absolute isolation is a theoretical abstraction. Real physical systems constantly interact with their environments, absorbing photons, reacting to magnetic fields, or adjusting to mechanical stress. To model these interactions, we introduce time as a variable, making the Hamiltonian a function of time, h of t. This alters our core question. Instead of measuring static energy levels, we track population movements, the probability a system transitions to another state after a disturbance. There is no single equation for every disturbance. Different types of external stimuli require specific mathematical frameworks to predict the resulting quantum response. We analyze how systems behave when a parameter shifts gradually, when they encounter a sudden shock, when driven by resonant waves, or when scattering into a continuum. Understanding these dynamic frameworks is what allows us to move from theoretical physics to the engineering of functional quantum hardware. We begin with systems where the disturbance is tied to a tunable external variable, rather than directly to a ticking clock. We denote this parameter as lambda. It represents a physical dial we can turn in a laboratory, such as the strength of an applied electric field, the strain on a crystal lattice, or the distance between two atomic nuclei. The Hellmann-Feynman theorem shows how a quantum state's energy reacts as the parameter lambda is continuously varied. The energy's rate of change equals the expectation value of the Hamiltonian's rate of change. This force-like response is calculated directly from the operator's derivative. This provides us with a significant computational shortcut. Because the derivative of the wave function cancels out for an exact eigenstate, scientists calculate the energy shift without explicitly differentiating the complex wave function itself. Computational chemists rely on this to optimize molecular structures. They track forces acting on nuclei, moving atoms step by step until the molecule reaches its stable geometry. By connecting electronic states to mechanical properties, this theorem forms the basis of density functional theory geometry optimization. When we apply disturbances as a direct function of time, we take a solvable base Hamiltonian and add a weak time-dependent perturbation, denoted as v of t. In real-world physics, the rate at which this perturbation is switched on dictates the final state of the system. In a sudden switching regime, a change is applied instantly. The system cannot adjust, forcing immediate excitations into higher states. Conversely, adiabatic switching introduces the perturbation slowly. This allows the eigenstate to smoothly deform into the new state, suppressing unwanted transitions. Suppressing transitions through this slow adiabatic process is an operational requirement for maintaining the stability of qubits during gate operations in quantum computers. The most common engineering disturbance is a periodic driving field, such as laser light, microwaves, or radio frequency radiation. An oscillating field only triggers a transition if it meets the resonance condition. The system absorbs energy in packets. A transition occurs efficiently only if the packet's energy, Planck's constant bar times frequency, exactly matches the gap between initial and final states. On resonance, a two-level system oscillates between ground and excited states, governed by the Rabi formula. The field's coupling strength sets the oscillation speed. Engineers use precise bursts. A pi pulse stops at the peak for full transfer, while a pi over 2 pulse creates equal superposition. Determining the exact duration of these pulses using the Rabi formula is how a single qubit gate is physically implemented. Discrete two-level models have limitations. In many devices, an initial state interacts with a massive number of final states. An electron can be ejected into free space or promoted into a broad semiconductor conduction band. In these cases, final states form a continuum. Because the final states are effectively infinite, the math shifts from calculating a single transition probability to calculating a continuous transition rate. Fermi's golden rule calculates transition rates into the continuum. The rate depends on the transition matrix element, measuring coupling strength. However, even with weak coupling, a transition is nearly instantaneous if there's a high density of available final states. These scattering rates allow engineers to predict electron charge mobility and the efficiency of modern solar cells. Finally, we must account for the background radiation that surrounds all quantum systems. Einstein categorized these interactions as absorption, spontaneous emission, and stimulated emission. In stimulated emission, an incoming photon triggers an excited state to drop, releasing a clone photon that matches the frequency and phase. This is the basis of lasers. However, states also collapse on their own through spontaneous emission. This means every excited state has a finite lifetime. Energy and time are conjugate variables in the uncertainty principle. If a state decays after a short interval, its energy becomes indeterminate. This manifests as spectral broadening. A rapid decay appears as a broad peak, while a long-lasting state produces a sharp, narrow spike. Balancing this energy lifetime equation is essential for designing pure color OLED displays and maintaining coherence in atomic clocks. These rules are not separate academic curiosities. They operate simultaneously inside modern hardware. Laser gain depends on optimizing the Einstein stimulated emission coefficient to overpower standard absorption, allowing a light beam to amplify as it travels through a medium. The color purity of OLED displays is bound by the lifetime uncertainty principle and Einstein decay rates, which dictate the narrowness of the emission bands. The ability to switch semiconductor logic gates relies on managing the scattering rates calculated by Fermi's golden rule. We have moved from identifying static, unmoving energy levels to modeling the complex, time-dependent movement of quantum populations. The mathematics of time-dependent transitions provides the functional rules for manipulating matter, light, and energy